Guys, welcome to another video. In this video, we're going to talk about PyTorch gradients. And before we get started, I just want to say I am not an expert in this stuff. I just enjoy making engaging YouTube videos. A lot of my content is pulled from ChatGPT, so please just do your own research. But if you want an overview, stick around. So think of a car, and a car has an automatic transmission and a manual transmission. Now, to just run any live model, you can use the automatic, and that's fine for most of the case. But if you want to see how stuff works underneath the hood, you need to do the manual transmission. And that's what I'm going to show you today with respect to gradients. So to motivate this, let's look at an example. Here's a function, single variable function, and it represents a loss that we want to minimize. So y equals x squared minus 4x plus 3. If we look at this function, we see that its minimum is at x equals 2, which is indicated by the green vertex. And at that value, the value y corresponds to -1. So what we want to do is we want to start at an arbitrary point, let's say x equals 0, and apply gradient descent repeatedly until we find the minimum value. So let's open up a Google Colab notebook. I imported Torch, and we're going to start with defining x. So x here is our input, and we want it to start at 0. Now, we're not just going to use a scalar, because scalars cannot be tracked by the gradient computation graph of PyTorch. So instead, we have to put it into a tensor. And we also have to make sure that it's being tracked by, that it's a gradient that's being tracked. And that's why we say it requires grad equals true. Then we'll write the function x squared minus 4x plus 3. And when we print out this value, we see that y is 3. So we have input x, we're passing it through a function f, and we get a y. What we're interested in is y dy of dx. So what we're going to do now is we're going to call backward on the loss function, which is y. And this is going to compute the gradients of everything that feeds into x. In other words, it's going to be doing something called backwards propagation. So the leaf tensors, which are x, which are tensors created directly by the user, will have their gradient updated, assuming that requires grade is equal to true. So let's go ahead and print the gradient. And you'll see that it's -4. And that kind of aligns with what it should be. If you look at the graph, at point x equals 0, the slope is pretty steep in the negative direction. Okay, so we want to apply the gradient descent equation, which is we want to update x of 1, which is the new value, based on the current value of x, subtracted by some constant, and then the derivative of y with respect to x at value x naught. So here's the gradient descent equation. Print out the new value of x, and we see it's 0.4, which is what we would expect because we started at x equals 0, and then we go in the positive direction as y goes less, so somewhere around here. Okay, now we're going to recompute y. So y is going to be x, but now we're using a new value of x. And we're going to also call backward again. Now let's see what our value of x is. An error. We see that the tensor is not a leaf tensor. So originally x was a leaf tensor, and to recap for people that don't know, a leaf tensor means it was created directly by the user. But what we're doing here is we're actually not modifying x, we're creating a new variable x, and that is a computation of x, and which basically no longer makes it a leaf tensor. So to fix this, we need to tell it, don't create a new variable, but mutate the existing variable. And to do that, we replace the equals with a minus equals. So now what happens when we run it? Now we get another error. So now x here is a leaf variable, so that's okay, but it says that it's being used in an in-place operation. So what does that mean? It means, to understand this, we have to understand there's two types of operations that we generally do. There's the forward pass, which is this, and then which is basically passing the input through our functions until we get y. And then there's the update equation, or updating our input, or generally weights. So when we want to track gradients for the forward pass, but we don't want to track gradients for the update, because otherwise the gradients are accumulating. So to fix this, we say torch.nograd, and then do this. So let's try it now. So now we get negative 7.2. So good, we get a number. But note this doesn't seem quite right. So at value x equals 0, the slope is negative 4. And notice as you go further to the right, the slope gets shallower. So the slope should be between negative 4 and 0, but it actually got larger. And the reason is because we are actually accumulating the gradient and not resetting it. So what we need to do is we need to set the gradient to 0. So now when we apply it, we get negative 3.2, which is more reasonable because the slope has gotten shallower. Okay. Now we're going to apply the gradient descent equation again, which I'll paste in here, and print out the new value of x. So when we do that, we see x1 is 0.4, x2 is 0.72. So we're getting closer to the final value of x equals 2. Okay, so now I've taken this and I've written as a loop to be iterated on, say, 15 times. So first what we do is we compute y from x. Then we call backwards to do the backward propagation. And then we say, don't add this as part of your gradients, but mutate the value of x using the gradient descent equation. Then, since we don't want the gradients to accumulate, zero out the gradients. And lastly, print out the value of x and y. So if I go ahead and do this, you'll see that initially it starts out at 0.4 and then 3. And then by the time we get to the 14th, 15th iteration, x is 1.92, y is negative 0.99. And if you scroll up, that's exactly very close to where the green vertex is. Okay, so that's the manual perspective of how to do gradients in PyTorch. When you're actually writing models, it will be a lot easier. Thank you for watching.